let's look at our next example. This example and the last one we'll do in this video will both come from groups of permutations. So let's take a subset I of the set from 1 up to n. And let's let J be the complement of that subset. So be everything else from 1 up to n that's not an I. Let's let G be the subgroup of Sn that is the setwise stabilizer of I. So what does that mean? G is the set of all permutations in Sn where it takes an element of I, say little I in I, and it spits out sigma of I, which is some other thing in your set I. So it's straightforward to check that this actually is a subgroup of Sn. What are you doing? You're taking the elements of I and permuting them in some way, and you're taking the elements of J and permuting them in some way. So that's another way of saying that G is also the setwise stabilizer of J. So anything that takes in any element in your index set I and outputs something in that index set I also takes in something in the complement of I and outputs something in the complement of I. So one way to think about it is your permutation treats the elements from 1 up to n in two different sets. There's all the things in I, and then there's all the things not in I, and it permutes these and it permutes these. Okay, so there's another special subset inside of this setwise stabilizer we could look at, which is the pointwise stabilizer. So that'll be H, which will be all the permutations in Sn, so that sigma of I equals I for all elements little I in your index set. So it acts as the identity on this index set I. Nothing in that set I moves, and all the things outside of I in this complement J, those get permuted around in some way. Okay, and we can define the pointwise stabilizer of J analogously. So K will be all the permutations in Sn that fix everything that's in J. So the idea here is to apply the recognition theorem for direct products. So if we want to do that, we want to have two subgroups, H and K of a group G, where they're both normal and their intersection is trivial. So let's see that H and K are both normal subgroups of G. First, G is a set of permutations on 1 up through n, and it takes the things in the set I and outputs something else in the set I. So it takes the subset I and permutes its elements. Another way to say this is G acts on the set I. Clearly, G acts on the set from 1 up to n. I mean, it's a subgroup of Sn, but it also acts just on this subset I. So what does that give us? That gives us a homomorphism from G to the symmetric group on the elements of I. You put in an element, G in G, or sigma in G, and you get a permutation of the elements of I. All right, well, what does it mean to be in the kernel of this homomorphism? So sigma is in the kernel if and only if the permutation that you get from sigma is the identity permutation. So what does that mean? How does sigma permute the elements of I? Well, it has to fix all of the elements of I. So sigma is in the kernel of this homomorphism if and only if sigma of I equals I for every little I in your index set. But what is that? That is H. That's like the definition of H. It's this pointwise stabilizer inside the setwise stabilizer. So because it's the kernel of a homomorphism, we see that H is a normal subgroup of G. Okay, same idea for J. So elements inside of G, they permute around the elements of I, but they also permute around the elements of J. So G acts on J, and we get a homomorphism that takes in an element of G and outputs a permutation of J. So exact same idea as before. What is the kernel of this homomorphism? Oh, the kernel of this homomorphism is K. It's all the things where you have a permutation in G, you get a permutation of the elements in this set J, and it's the identity permutation. So what does that mean? Sigma of J equals J for all elements in your index set. So what does that mean? K is the kernel of this homomorphism, so K is a normal subgroup of G. So we've seen that H and K are two normal subgroups inside of G. If we want to apply this recognition theorem for direct products, we have to understand their intersection. So what does it mean for sigma to be in the intersection of H and K? Well, it's in H. So sigma of I equals I for all I in the index set. And it's also in K. So sigma of J equals J for all elements J in the set capital J. But this set capital J is the complement of I. So it's everything else in 1 up to n except I. So what does that mean? Sigma fixes everything in I, and it fixes all of the other things that are not in I. So sigma has to fix everything from 1 up to n. So that means that sigma is the identity. So what is the intersection of H and K? It is the trivial subgroup inside of G. So where are we? We have these two normal subgroups, H and K, inside of G, and we know that their intersection is the trivial subgroup. So the recognition theorem for direct products says that the internal direct product, HK, is isomorphic to the direct product H cross K. So in order to draw the conclusion that we want, all we have to do is say something else about what is this internal direct product. So I'll pause and erase, and then we'll see that the internal direct product is all of G. Let's finish our discussion of this example. Where are we? We know H and K are normal subgroups of G, and their intersection is trivial. So by the recognition theorem for direct products, the internal direct product, HK, is isomorphic to H cross K. But what is this internal direct product? So any permutation in G, so that means something that is in the setwise stabilizer of I, so it permutes the elements of I, and separately it permutes the elements of J. Well, this can be written as a composition of two permutations. One, where you permute the elements of I and you leave the elements of J fixed. And then another, where you permute the elements of J and you leave the elements of I fixed. And it's clear that because the orbits of size bigger than 1 in this these two permutations don't overlap at all, that they commute with each other. So this permutation sigma in G can be written as sigma J, something where you permute the elements of J and leave the elements of I fixed, and then times something that's where you permute the elements of I and you leave the elements of J fixed pointwise. So what is that saying? That's saying that sigma is a product of something in H times something in K. So in particular, it's in HK. So this internal direct product, HK, is the entire group G. So now by the recognition theorem, G is isomorphic to H cross K. So let's just look a little more deeply at what are H and K. Like, what are those groups? Let's just note that if you have a permutation of J, that gives a permutation in H. So it gives a permutation of all of the elements from 1 up to n, where you have your permutation of the elements of J, and then you just fix everything in the complement of J. So you fix everything in I. So you get a permutation in H because you're fixing the things not in J. Similarly, if you have a permutation of the elements of I, then just fix all of the elements not in I, and you get a permutation in K. So what does that mean? H is isomorphic to the group of permutations of the elements of J. And K is isomorphic to the group of the permutations of the elements of I. So in particular, if you just pick a size for J, then you can see now that all the symmetric groups on a set of size m are isomorphic to each other. So if the size of J is m, then H is isomorphic to Sm, and K is isomorphic to this S, whatever the size of I is, which is n minus m. So in this way, using the recognition theorem, we've seen that this G is isomorphic to Sm cross Sn minus m. So we found the subgroup inside of Sn that is isomorphic to a direct product of two smaller symmetric groups. So I'll pause and erase, and then we'll give one more example that comes from groups of permutations. Let's talk about the final example of this video. And this builds pretty directly on the previous example. So let's pick sigma to be any permutation in Sn. And now we're going to define a set I as a subset of 1 up to n that comes from sigma. Comes from sigma how? This set I is going to be the set of all little I from 1 up to n, so that sigma fixes I. Sigma of little I is little I. And what we want to do in this example is study the centralizer in Sn of this permutation sigma. So we're going to name that. We'll call that C. So here's an exercise for you to do. You can check that C stabilizes the set I, and C stabilizes the set J, the complement of I as well. So what does that mean? If you have any permutation in the centralizer of sigma, so any permutation that commutes with this permutation sigma, then that permutation has to move around the elements inside of I and also move around the elements outside of I. But you can't have a permutation in the centralizer that, for example, takes something in I and sends it to something in J. So this is pretty straightforward to prove. What you could do is suppose you have a permutation in the centralizer that takes some element in the set I and sends it to some element not in I, and then find a contradiction with the assumption that that permutation commutes with sigma. Okay, so now we have a group of permutations that stabilizes I and stabilizes the complement of I. So the previous example was all about that, this setwise stabilizer of I and J. So what that means is that C is a subgroup of this setwise stabilizer of I. But in the last example, we saw that the setwise stabilizer of I is isomorphic to a direct product, H cross K, where H and K were defined as in this previous example. So if C is isomorphic to a subgroup of this setwise stabilizer, then it's isomorphic to a product of H, which is the pointwise stabilizer of the subset I, and K, which is the pointwise stabilizer of the subset J. Okay, so let's first note this permutation sigma that we use to get this whole thing started is an element of this H, as we defined in the previous example. Why? Because sigma of I equals I for all I in the index set. And now, what do we know? Well, we know that inside of the setwise stabilizer of I, you can write every element as a product of two permutations, one that first permutes the elements of J, and then another that just permutes the elements of I. So another way to say this is because C is contained in this setwise stabilizer of I, any alpha in C can be written uniquely as a product alpha J times alpha I, where alpha J is in the pointwise stabilizer of I. So it permutes around the things in J and leaves the things in I fixed. And then alpha I, which is in K, it fixes all the things in J and it permutes the elements of I around. Okay, so we have a nice way of writing a product in here. So now let's get back to what do we know about this centralizer. If tau is in K, what does that mean? Well, that means that tau fixes all of the things that are in 1 up to n, but not in I. And this means that sigma and tau commute, right? Because the sigma fixes all of the things that are in I, and it permutes around the things that are not in I. Tau fixes all of the things that are not in I and permutes around the things in I. So the orbits of size bigger than 1 for each of these permutations don't intersect at all. So that means they commute. So what does that mean? Any tau in K commutes with sigma. So in particular, it's in the centralizer. So that means that K is a subgroup of the centralizer. So now what do we know about the centralizer? Well, it's isomorphic to a subgroup of this direct product, and it contains all of K. So what does that mean is we can write the centralizer as a direct product, as anything that commutes with sigma that is in H. So the things that pointwise fix the elements of I, like this, cross anything in K, because everything in K commutes with this sigma. So in particular, we know that H is isomorphic to Sj, the set of permutations of J. So sigma gives a permutation of the elements of J. It fixes all the things in I. So just forget about the things in I. Sigma gives a permutation of the elements of J. So we can think of the centralizer in Sn as a direct product of the centralizer of sigma inside the set of all permutations of J cross all the permutations of the elements of I. So this is true for any permutation sigma. But if we zoom in on the case where sigma is an M cycle in Sn, something that we studied earlier, particularly like when we talked about sizes of conjugacy classes in A5, well, if sigma is an M cycle in Sn, then what does that mean? Well, the set of things that are in I are everything except those first M elements. And the set of things that are in J are just the M elements of the M cycle of sigma. So what is the centralizer of an M cycle in Sm? It's just the cyclic subgroup generated by sigma. And then what is Si in this case? It's all the other, I is all the other n minus m elements. So we see in this case that the centralizer of our permutation sigma in Sn is a direct product of the cyclic subgroup generated by sigma times Sn minus m, the permutations on the other n minus m elements. And this is something we proved earlier, but now we're understanding it in a different way.